Pluto, once considered part of our planetary system, still remains a far-off and intriguing celestial object. Recently, well-known astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the scientific spotlight, proposing a startling new theory: the possibility of Pluto colliding with Neptune. This raises a series of important questions. How could such a catastrophic event unfold, and what consequences would it bring? Is this just a fascinating yet unlikely theory, or could there be more to it? Join us as we investigate the potential impact of a Pluto-Neptune collision. Pluto, which was once classified as a planet but later redefined as a dwarf planet, continues to captivate the scientific community. Its unusual orbit makes it a subject of ongoing research. According to recent discoveries from leading scientists, Pluto's orbit crosses dangerously close to Neptune's path, raising alarms about a possible collision. But how feasible is such an event? Pluto's journey around the Sun is unique among the planets. It takes a lengthy 248 years to complete one full orbit. As a result, since its discovery in 1930, Pluto has not yet finished a single full orbit. In addition to its long orbit, Pluto's path differs significantly from the nearly circular orbits of the other major planets, as it is tilted at a 17 degrees angle relative to the plane of the solar system. This results in a much steeper trajectory compared to the other planets. A particularly fascinating aspect of Pluto's orbit is its periodic intersection with Neptune's orbit. For approximately 20 years in each orbit, Pluto is closer to the Sun than Neptune, which is surprising given their positions in the solar system. This naturally leads to the question: why has Pluto not collided with Neptune? The answer lies in the gravitational forces of other planets. When astronomers first studied Pluto's orbit, they were confused by its unusual characteristics. Unlike other planets, whose orbits mostly lie near the ecliptic plane, Pluto's orbit is tilted and curved. This anomaly raised even more questions when astronomers realized that Pluto's path intersects Neptune's. Studying this occurrence illustrates the complexity of space dynamics, especially when multiple celestial bodies influence each other's motion. The three-body problem in space is a challenge that describes the difficulty of predicting how three celestial bodies, such as Pluto, Neptune, and the Sun, interact gravitationally. Pluto's orbit is chaotic. Even the smallest variation in its initial conditions could lead to dramatic changes over time. However, this chaos has been found to stabilize over long periods. Simulations have shown how the gravitational influence of larger planets like Neptune, Jupiter, and Saturn helps maintain Pluto's orbit over billions of years, preventing destabilization. Without these large planets exerting their gravitational forces, the solar system would be far more chaotic. Pluto's orbit offers a clear example of both disorder and stability in celestial mechanics. While its path is irregular, it has remained surprisingly stable due to the forces exerted by neighboring planets, particularly Neptune. Predicting the future behavior of such an unstable orbit, like Pluto's, is incredibly difficult, as the inherent unpredictability of these systems makes long-term forecasts uncertain. This brings us to the question: why are respected astrophysicists like Neil deGrasse Tyson and Michio Kaku now sounding alarms about a potential Pluto-Neptune collision, even though the stabilizing forces are well known? Despite the various forces keeping Pluto's orbit in check, they express serious concern about the possibility of such a collision. Should it occur, the consequences would be catastrophic. The collision would release an immense amount of energy, most likely obliterating Pluto, due to its smaller size and icy composition. The resulting debris from the impact could be scattered throughout the solar system, potentially endangering other planets and their moons. For Neptune, the impact could affect its atmosphere and even alter its orbit, depending on the scale of the collision. Michio Kaku, a theoretical physicist known for his work in string theory and space exploration, offers a unique perspective on the situation. His understanding of gravitational interactions and orbital dynamics helps us appreciate the deeper connections between celestial mechanics and theoretical physics. Knowing how bodies like Pluto interact gravitationally is essential for future space missions, as it not only aids in exploring distant planets, but also helps predict and prevent potential dangers within the solar system. The implications of a Pluto-Neptune collision go beyond the immediate destruction of two celestial bodies. It could also provide crucial insights into high-energy physics and gravity. The event might create conditions where string theory predictions become observable, offering explanations for how fundamental forces and particles behave in extreme environments. While the physical impact on Earth would be minimal, given the vast distance between Pluto and our planet, the scientific consequences could be monumental. It would provide a rare opportunity to observe and test key principles of string theory and other branches of physics. Pluto's orbit, with its distinct features, continues to fascinate scientists, offering a glimpse into the complexities of celestial dynamics. The reclassification of Pluto as a dwarf planet sparked much debate, but recent discoveries about its orbit have reignited interest in its role in the solar system. Both Tyson and Kaku have raised alarms about the potential risks posed by a collision between Pluto and Neptune, stressing the delicate balance of forces involved. Pluto's path, with its steep inclination and tilted orbit, defies conventional planetary motion. Unlike the nearly circular orbits of the major planets, Pluto's orbit intersects Neptune's, complicating predictions about future interactions. The gravitational forces exerted by planets like Neptune are crucial in maintaining Pluto's orbit, preventing further chaos in the system. Despite its irregular orbit, Pluto's path has remained surprisingly stable over long periods, thanks to the gravitational influence of neighboring planets. While mathematical models and simulations play a key role in forecasting the movements of celestial bodies, they also reveal the complexities of gravitational interactions. Although Pluto's orbit may be unpredictable over centuries, it remains relatively steady in the broader context of the solar system's gravitational framework. While the likelihood of a Pluto-Neptune collision remains low, it serves as a reminder of the unpredictable nature of the cosmos. The warning from experts like Tyson and Kaku emphasizes the constant flux of the solar system. While such a collision seems unlikely in the near future, it underscores the delicate balance of forces governing the movement of celestial bodies. Beyond its scientific importance, the study of Pluto holds practical significance for future space exploration. NASA's New Horizons mission, launched in 2006, provided us with unprecedented images and data from Pluto and its moons during its historic flyby in 2015. These findings revealed new details about Pluto's surface, including vast frozen nitrogen fields and expansive water ice plains, expanding our understanding of geological processes on distant worlds. The success of the New Horizons mission also demonstrated the importance of international collaboration in exploring distant celestial bodies. By studying Pluto, scientists have gained valuable insights into the outer reaches of the solar system, which could guide future missions to other distant objects. The ongoing debate over Pluto's status as a dwarf planet reflects larger questions about the classification of celestial bodies. Although Pluto meets several criteria for being a planet, its reclassification raises important discussions about the evolution of science and the way astronomical objects are categorized. Investigating Pluto's orbit and its interactions with other planets enhances our understanding of planetary motion, celestial mechanics, and the formation of the solar system. By studying Pluto's unique orbit, we can better comprehend the dynamics of other distant celestial bodies. The discovery of Pluto also led to the identification of the Kuiper Belt, a region beyond Neptune populated by small icy objects. Research into Pluto's orbit offers clues about the gravitational forces that may have influenced the early formation of planets. This knowledge is essential for developing theories about the solar system's origins and the processes that shape planets over time. Additionally, understanding these celestial dynamics will play a vital role in future space exploration, particularly when it comes to identifying potential targets for upcoming missions. Although the likelihood of a Pluto-Neptune collision is low, it serves as a reminder of the unpredictable nature of space. As we continue to explore the outer solar system and beyond, the study of planetary orbits and celestial dynamics will remain a core area of research. Pluto's unique orbit offers valuable insights into the forces at work within our solar system, and the ongoing investigation into its behavior provides key information about the broader workings of the universe. With every discovery, we refine our understanding of the cosmos, uncovering the mysteries of distant worlds and deepening our understanding of the fundamental principles of the universe. In addition to its role in enhancing our understanding of planetary dynamics, Pluto's orbit offers a unique opportunity to study the forces that shape the solar system. As a dwarf planet, Pluto has been the focus of much discussion not only due to its orbit but also because of the debate surrounding its classification. Its journey through space sheds light on the challenges of categorizing celestial bodies and the complexities of their behaviors. The ongoing research into Pluto's orbit, its interactions with other planets, and the nature of its orbital characteristics contributes to a deeper understanding of the solar system's architecture. The study of Pluto also provides insight into the broader field of celestial mechanics. Celestial mechanics refers to the study of the motions of celestial objects under the influence of gravity, and Pluto's unusual orbit presents an intriguing case for scientists. Its path is a striking example of how gravitational forces between planets and other bodies in the solar system affect the movement of smaller objects. By studying how planets like Neptune influence Pluto's orbit, we gain a clearer picture of the stability and evolution of the entire solar system. One of the critical factors in maintaining the stability of Pluto's orbit is its resonance with Neptune. Although their paths intersect periodically, they are in a locked resonance that prevents a direct collision. This resonance, known as a 2:3 orbital resonance, ensures that for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This mechanism acts like a safeguard, preventing the two bodies from ever colliding despite their intersecting paths. This phenomenon illustrates how complex interactions between different bodies can lead to stability, even in seemingly chaotic situations. In the broader context of space exploration, Pluto's orbital behavior also underscores the importance of studying distant celestial bodies to learn more about our own solar system's formation and evolution. As astronomers continue to investigate objects like Pluto, they not only gain knowledge about these far-off worlds but also piece together the story of how our solar system came to be. This understanding is critical for future missions to distant planets, asteroids, and other celestial objects that may hold clues about the early solar system and the conditions that led to the formation of planets like Earth. The research into Pluto's orbit also complements the study of other regions in the solar system, such as the Kuiper Belt. The Kuiper Belt is a vast region beyond Neptune, populated by small icy bodies, many of which have similar characteristics to Pluto. By understanding Pluto's orbit and how it interacts with Neptune, scientists can make predictions about the behavior of other objects in the Kuiper Belt. This has implications for future space missions aimed at exploring these distant regions and further expanding our knowledge of the solar system's outer edges. Moreover, the discovery of Pluto also played a significant role in the development of our understanding of planetary formation. By studying the gravitational interactions between Pluto and Neptune, scientists have gained insights into how planets and smaller bodies in the solar system may have formed and evolved. This knowledge is essential for developing theories about how the solar system itself was formed and how similar processes might occur in other star systems. The study of Pluto's orbit and its interactions with other celestial bodies may offer valuable information for understanding the broader processes of planetary formation across the universe. In addition to these scientific advancements, the exploration of Pluto also serves as a testament to the power of human ingenuity and international collaboration. The success of missions like New Horizons demonstrates the remarkable progress made in space exploration technology. The data collected from Pluto and its moons has expanded our understanding of the geological features of distant worlds, revealing previously unknown details about their surfaces. These findings not only contribute to our knowledge of Pluto, but also serve as a stepping stone for future exploration of other distant objects in the solar system. The technological advancements required for deep space exploration are another key aspect of studying Pluto. Missions like New Horizons rely on cutting-edge technology to collect data from planets and moons that are located billions of miles away from Earth. These advancements are essential for exploring distant regions of the solar system and beyond, where traditional space probes would be ineffective. The ability to send spacecraft on long-duration missions, like the journey to Pluto, represents a significant achievement in space exploration and demonstrates the potential for future missions to even more distant and mysterious parts of the universe. As we continue to explore the outer regions of the solar system and beyond, the study of Pluto remains a cornerstone of planetary science. The knowledge gained from examining Pluto's orbit, its interactions with other celestial bodies, and the broader dynamics of the solar system has profound implications for our understanding of space and the universe. Every new discovery about Pluto offers a glimpse into the vastness and complexity of the cosmos, furthering our appreciation of the forces at work in the universe. Pluto's status as a dwarf planet and its unusual orbit also raise important questions about how we define and categorize celestial bodies. While Pluto's reclassification sparked debates among astronomers, it also highlighted the need for more refined criteria for distinguishing between planets and other types of celestial objects. This ongoing debate about Pluto's classification reflects the evolving nature of science, where new discoveries often lead to rethinking old assumptions and refining our understanding of the natural world. The study of Pluto also provides important lessons for future space exploration missions. As we develop new technologies and techniques for exploring distant planets and moons, the challenges posed by Pluto's remote location and unique orbital characteristics will continue to inform the development of spacecraft, mission strategies, and exploration tools. By learning from Pluto's example, scientists can better prepare for future missions to explore other distant worlds, both within our solar system and in other star systems. The possibility of a collision between Pluto and Neptune, while still a distant and unlikely scenario, serves as a reminder of the dynamic and ever-changing nature of the cosmos. The forces at play in the solar system are complex and difficult to predict, but studying these interactions helps us understand the underlying principles that govern the movement of celestial bodies. The scientific community's growing interest in Pluto and its orbit reflects a broader desire to uncover the mysteries of the universe and gain a deeper understanding of the forces that shape the cosmos. In conclusion, Pluto's orbit continues to captivate scientists and space enthusiasts alike, offering valuable insights into the workings of the solar system and the broader universe. While the likelihood of a Pluto-Neptune collision remains low, the study of this possibility highlights the unpredictable nature of space and the complexities of celestial mechanics. As we continue to explore the outer reaches of the solar system and beyond, Pluto's story serves as a testament to the power of scientific inquiry and the enduring quest to understand the mysteries of the cosmos.